Right now, racing past the orbit of Jupiter and plunging headlong into the freezing outer darkness of our solar system, a frozen ghost is carrying a chemical code that breaks our understanding of the early Milky Way. Discovered plunging through the void at speeds that defy the gravitational grip of our sun, this object is not just another piece of rock and ice from the local neighborhood. It is a wanderer, born in the faint, frigid dawn of the galaxy, carrying the chemical fingerprints of an era long before our solar system even existed. We thought we understood the composition of primordial comets, but the data pouring in from our most advanced space telescopes over the last few months has revealed something completely unexpected. The atmospheric signatures do not match the local interstellar medium. The isotopic ratios contradict the standard models of galactic chemical evolution. We are looking at a relic that has drifted through the absolute silence of deep space for up to 12 billion years. A time capsule that somehow survived the turbulent youth of the universe, only to graze our home and vanish again. What exactly is this object made of? And why does its deeply buried chemistry suggest that the raw ingredients for life might have been stirring in the dark, chaotic stellar nurseries billions of years before the Earth was even a thought? The story of this extraordinary encounter began in the summer of 2025, when vigilant sky watchers utilizing automated wide-field survey telescopes designed to scan the darkest corners of the night detected a faint, fast-moving smudge of light. Initially, it appeared as just another transient blip against the backdrop of distant stars. But as astronomers began to map its astrometric positions, linking right ascension and declination measurements over several nights, the resulting trajectory calculation sent a shock wave through the global astronomical community. The mathematical curve of its path was not a closed ellipse, it was a hyperbola, characterized by an extreme eccentricity that completely ruled out a gravitational binding to our sun. Furthermore, its incoming velocity vector was staggering. As it screamed into our solar system, it was clocked at over 220,000 kilometers per hour relative to the local standard of rest. This blistering speed is a definitive signature of an object arriving from the deep interstellar void, making it only the third such visitor ever confirmed by human observation, following in the historic footsteps of Oumuamua and Borisov. If you are fascinated by these unraveling mysteries of the cosmos and want to follow along as we decode the hidden architecture of the universe, consider subscribing to the channel. We continually explore the boundaries of astrophysics to bring you the cutting edge of space science. When the velocity and trajectory data of this new object, officially designated as the third interstellar comet and named Atlas, first hit the public databases, whispers immediately began to spread across the internet. The sheer kinetic energy of the object, combined with a puzzling lack of early outgassing as it crossed the frost line of our solar system, sparked wild speculation. Could this be something engineered? Was it an alien probe, masquerading as a dormant comet, utilizing a perfectly calculated gravity assist to survey our star system? The exactness of its approach and its unusually dark, unreflective surface led some to wonder if we were looking at artificial interstellar architecture. But the astronomers and data analysts knew better, or at least they believed they did. The kinematic data screamed of a natural, albeit highly unusual, interstellar origin. The trajectory indicated that it had been drifting through the galactic disk for an incomprehensible amount of time, a silent witness to the rotation of the Milky Way. Yet, the true shock was not its speed or its trajectory. The real mystery lay buried beneath its irradiated crust, waiting to be illuminated by the most powerful infrared eye ever built by humanity. The turning point in this investigation occurred in late 2025, specifically in December, when the interstellar comet Atlas swung past the Earth at a respectful distance of 270 million kilometers. This proximity provided a fleeting golden window of opportunity. The James Webb Space Telescope was commanded to turn its massive gold-coated beryllium mirrors toward the fading visitor. Observing a fast-moving, relatively small object at that distance requires immense precision, as the telescope must track the comet's rapid apparent motion across the sky, while simultaneously gathering enough ancient photons to build a reliable spectrum. Webb drank in the infrared breath of the comet, utilizing its near-infrared spectrograph to break apart the light reflecting off and emitting from the faint coma of gas and dust surrounding the nucleus. In astrophysical spectroscopy, we do not look at pictures. We look at light broken down into a barcode of missing colors. When sunlight hits the evaporating gases of a comet, the molecules in that gas absorb specific frequencies of infrared light. The chemical bonds within the molecules vibrate, bend, and stretch at very precise resonant frequencies. By mapping exactly which wavelengths of light are absorbed, we can determine exactly which molecules are present in the gas. When the raw spectral data from the December observation was downloaded and processed, the results were entirely unexpected. The spectrum that poured out was astonishing, challenging our baseline assumptions about interstellar chemistry. The first major anomaly observed in the data was the presence of water vapor that was shockingly rich in heavy deuterium. To understand why this is so critical, we have to look at the physics of isotopes. A standard hydrogen atom consists of one proton and one electron. Deuterium is an isotope of hydrogen that contains an extra neutron, making it twice as massive. In the vast oceans of Earth, the ratio of deuterium to standard hydrogen is relatively low and well documented. In the comets that originate from our own distant Oort cloud, that ratio is generally higher, reflecting the cold conditions of our primordial solar nebula. But the ratio found in the coma of the interstellar comet Atlas was off the charts. It was heavily skewed in a way that points to a very specific, extreme formation environment. In the ultra-cold environments of giant molecular clouds and early protoplanetary disks, chemical reactions do not behave the way they do at room temperature. The zero-point energy of a molecular bond involving deuterium is slightly lower than the zero-point energy of a bond involving regular hydrogen. When the ambient temperature drops to near absolute zero, specifically hovering around 30 Kelvin, the tiny energy difference between a hydrogen bond and a deuterium bond becomes a massive thermodynamic advantage. At 30 Kelvin, chemical networks overwhelmingly favor the incorporation of heavy deuterium into water ice and organic molecules. The extreme deuterium enrichment detected by the James Webb Space Telescope strongly implies that the core of this comet was forged in an environment where temperatures plummeted to 30 Kelvin and stayed there while the ice aggregated. We are picturing a protoplanetary disk around some long-dead first-generation star, far from the warming radiation of the galactic center. But the deuterium ratio was only the first layer of the puzzle. As analysts scrutinized the spectral absorption lines corresponding to carbon dioxide and trace hints of methane, another profound contradiction emerged. The carbon isotopes were skewed entirely far from anything forged in our local stellar neighborhood. Carbon, the fundamental building block of complex chemistry, primarily exists in two stable isotopes, carbon-12 and carbon-13. Carbon-12 is synthesized in the cores of stars through the triple alpha process, where 3 helium nuclei are fused together. Carbon-13 is produced later, primarily as a byproduct of the carbon-nitrogen-oxygen cycle in slightly older, more evolved stars. Over the lifespan of a galaxy, as generations of stars are born, burn, die, and expel their enriched guts into the interstellar medium, the ratio of carbon-12 to carbon-13 steadily changes. The galaxy effectively pollutes itself with heavier isotopes over time. By measuring the carbon isotopic ratio In a celestial object, astronomers can effectively read a chemical clock that tells them when that object formed in the history of the galaxy. The carbon isotope ratio detected in the outgassing coma of the interstellar comet Atlas was extraordinarily high in carbon-12 and completely deficient in carbon-13. This composition screams of formation in a metal-poor cradle. In the terminology of astrophysics, any element heavier than helium is referred to as a metal. A metal-poor environment is one that has not yet been enriched by many successive generations of dying stars. The severe lack of carbon-13 and other complex heavier isotopes in the comet's spectrum points to an origin date potentially 10 to 12 billion years ago. This staggering age places the birth of this wanderer in the deep cosmic past. Long before the thin disk of the Milky Way, the spiral structure we call home, had fully settled into its current form. 10 to 12 billion years ago, the universe was barely out of its infancy. The Milky Way was a turbulent, chaotic nursery of newborn stars, massive collisions, and swirling, pristine gas clouds. The stars forming in that epoch, known to astronomers as population 2 stars, were massive, bright, and lived short, violent lives. The data suggests that this comet aggregated in a protoplanetary disk around one of these ancient suns. It is a piece of the thick disk of the galaxy, the older, more diffuse halo of stars that surrounds the younger, flatter, thin disk where our solar system resides. Imagine the scene of its birth. A massive bright star illuminates a swirling disk of gas and dust. Because the metallicity of the universe is still so incredibly low, the dust grains are primitive, mostly silicates and simple carbon compounds. Yet, in the darkest, coldest outer regions of this ancient disk, shielded from the fierce, ultraviolet radiation of the central star, dense ices loaded with volatiles began to form. The temperatures hovered near absolute zero. In this quiet, freezing dark, the very first chemical steps toward complexity were taking place. The ice mantles coating the dust grains became microscopic laboratories. As the James Webb Space Telescope mapped the comet's strange chemistry, it found not just simple water and carbon dioxide, but the faint spectral signatures of complex organic molecules. Prebiotic molecules might already have been stirring there, in the galaxy's wild youth, seeding possibilities that would take eons to play out elsewhere. This raises a profound question. If the complex chemical precursors required for life were already forming in the ultra-cold disks of first-generation stars 12 billion years ago, how common is the deep biological potential of the universe? We are not just looking at a clump of ice and rock, we are looking at a messenger from cosmic childhood. But the object we see today is not exactly the same object that formed in that primordial disk. The data reveals a duality in its nature. While the outgassing vapor tells the story of its pristine interior, the physical behavior of the comet hints at a violently altered surface. When it first entered our solar system, it did not immediately light up with a bright coma, like a typical local comet would. It remained stubbornly dark until it crossed well inside the orbit of Mars. This delayed reaction is a direct consequence of its immense journey. For 10 to 12 billion years, this frozen time capsule drifted through the interstellar void. Deep space is often thought of as an empty, peaceful vacuum, but from a chemical perspective, it is a harsh, relentless radiation environment. The space between the stars is flooded with galactic cosmic rays, incredibly high-energy protons, and atomic nuclei accelerated to near the speed of light by the shock waves of ancient supernova. For billions of silent years, these cosmic rays bombarded the surface of the Wanderer. When a high-energy proton slams into a matrix of water, carbon dioxide, and methane ice, it breaks the molecular bonds in a process known as radiolysis. The lighter hydrogen atoms are liberated and gradually escape into space, while the heavier carbon, oxygen, and nitrogen atoms are left behind to recombine into increasingly complex, dark, durable macromolecules. Over deep geological time, this relentless cosmic ray weathering baked the outer layers of the comet into an unrecognizable, asphalt-like crust. This thick, irradiated shield of complex organics served as a thermal armor, preventing the volatile ices buried deep within from sublimating away during its brief encounters with the diffuse warmth of interstellar gas clouds. Only when the comet plunged deep into the steep gravitational well of our solar system, feeling the intense, rising thermal radiation of our modern sun, did the heat finally penetrate that ancient crust. The pristine ices beneath, untouched since the dawn of the galaxy, began to sublimate, cracking the dark shell and venting the ancient gases into space for our telescopes to intercept. The core still whispers secrets from the beginning, protected by a surface that bears the scars of eternity. The interpretation of this data challenges existing models of how objects are ejected from their home systems. For a comet to leave its parent star, it must be gravitationally perturbed, usually by the migration of giant planets within its original system, or by the close passage of another star. If this comet was ejected 10 to 12 billion years ago, it means that giant planet formation, or at least the formation of massive perturbing bodies, was already occurring around metal-poor stars in the chaotic early galaxy. The parent sun that birthed this comet likely died ages ago, expanding into a red giant and shedding its outer layers before collapsing into a dim, cooling white dwarf. Its ashes have long since been scattered across the thick disk or lost to the intergalactic medium. Yet this tiny frozen fragment survived, escaping the death of its system to wander alone in the endless night. As we continue to analyze the telemetry and the spectral absorption bands, we must confront what remains uncertain. We know the object is ancient based on its isotopic ratios, but we cannot precisely retrace its kinematic path to pinpoint the exact star cluster that birthed it. The galaxy has rotated dozens of times since this object began its journey. The gravitational potential of the Milky Way is not perfectly smooth. It is filled with giant molecular clouds, spiral arms, and dark matter subhalos that subtly alter the trajectory of a wandering object over billions of years. Attempting to run the orbital mechanics backward for 12 billion years is a chaotic mathematical problem with no unique solution. We may never know exactly where it came from. All we have is the chemical memory locked within its ice. By March of 2026, the window for detailed observation is rapidly closing. The interstellar comet Atlas is already racing beyond the orbit of Jupiter. Its incredible hyperbolic excess velocity ensures that the sun's gravity is utterly powerless to pull it back. It is on a one-way trajectory out of our neighborhood. Soon, it will skim past the orbital distances of Saturn, then Uranus, and finally Neptune. Each planetary orbit it crosses marks a fading milestone as it hurtles back into the abyss. The Hubble Space Telescope recently caught a final glimpse of its delicate coma, revealing that the outgassing is already beginning to shut down. As the solar radiation drops off exponentially with distance, the temperatures on the comet's surface are plunging back toward the interstellar baseline. The ancient crust is freezing solid once again, sealing the primordial ices back inside their dark vault. The full story of this object slips away with every passing day. The James Webb Space Telescope mapped its strange chemistry and provided us with a revolutionary dataset, but the sheer volume of questions generated by this brief encounter will take decades to fully resolve. Astronomers will spend years running advanced chemical kinetic models to understand exactly how those specific isotopic ratios could form in a low metallicity environment. They will debate the precise mechanisms of cosmic ray weathering and how deeply the radiation could have penetrated the ice over 12 billion years. They will refine their models of the early Milky Way to account for the presence of complex chemistry in the earliest stellar nurseries. What remains for us, as observers of this cosmic event, is the profound shiver of contact. We brushed against something ancient, something that predates planets, oceans, and life as we know it. We intercepted a piece of the universe's own memory, briefly illuminated by our telescopes, before vanishing forever into the dark. It forces us to realize that our solar system is not an isolated island, but a porous environment, continually washed by the debris of the wider galaxy. How many millions of such objects have passed through our inner solar system unseen throughout Earth's history? How much of the water and organic material currently on our own planet might have been seeded by similar ancient wanderers striking the early Earth? The implications stretch far beyond a simple astronomical observation. They touch upon the very origins of our existence and the interconnected nature of the cosmos. If you found this deep dive into the primordial chemistry and the orbital mechanics of the universe valuable, please leave a like on the video to help surface this scientific research to more curious minds. Your engagement helps us continue to unravel these complex astrophysical narratives. As the interstellar comet Atlas crosses the heliopause and leaves the magnetic bubble of our solar system behind, it will return to the silent, freezing void from which it came. It will not return. Its trajectory will carry it through the interstellar medium for billions of years more, and somewhere out there, in another star system, in another time, perhaps another eye will catch this same wanderer. Perhaps another civilization, wielding their own grand telescopes, will calculate its hyperbolic path, capture its infrared spectrum, and feel the same quiet awe at holding a fragment of eternity. Or perhaps it will simply keep sailing, silent and alone, unobserved and undisturbed, carrying its ancient cargo through the endless night until the galaxy itself fades into the dark.